Hello, and thank you for joining us. Welcome to this webinar event. It is one of many such webinar-based professional development events brought to you by Texas Instruments Australia as part of our ongoing support for teachers in the classroom. Today's topic, using data capture to help teach calculus. And our presenter, Stephen Crouch. Many of you who may have seen before, featuring in our webinars, or also at face-to-face training events. Good evening, Stephen.
Good evening, Brian. Good evening, everyone.
Great to have you with us once again, Stephen. We can see on your bio here that you cover all of the senior mathematics topics, as well as a bit of the physics and other sciences. The mention here of your use of technology, having done that both as a student and now as a teacher, but also in your presentation at conferences. Participants, we are set for a terrific webinar this evening. I have seen Stephen go through these main ideas both before in a webinar, but also live at the Learn, Energize, Connect events. That's what that LEC stands for. And I can assure you that he not only expertly captures the data, but he certainly captured and held a packed room of eager teachers to learn more about this.
Excellent. Thank you. Thank you, Brian. Appreciate it. Are you able to see my screen?
We can indeed. What is data capture?
Excellent. Okay, so in my experience, it feels like data capture is quite a misunderstood feature of the TI-Nspire system. Most, if not all, teachers would have either little to no experience regarding data capture. It is actually quite a tricky concept to navigate around. So my aim today is to basically make it as easy as possible to, number one, learn it, but number two, also master it and really use it with your classes to really showcase the capabilities of TI-Nspire, as well as all the different concepts that it captures. So first of all, it's pretty much the key to unlocking the dynamic visualization or interactivity that the TI-Nspire system has. And basically, you can do things like this. So you've seen these questions previously where you have circles and or shapes or parabolas or things like that, and you're trying to maximize the area or minimize distance and that sort of thing. So a static diagram like that can be drawn on a whiteboard can actually be converted into a really nice dynamic feature using data capture, as you can see with that interactivity I've got there. And once you start messing around with these shapes over here, you end up with graphs that look like that. And you can see with the visuals that you've got over there, that diagram right there is purely the output of a data capture program. So simple things like that can really be brought to life using this data capture. So I'd just like to quickly go over how the data capture workflow works, and then I'll go through a couple of examples to show you how that works, and then go to some more complicated examples. So first of all, what happens is an object gets created in either the graph or geometry application. Those are the icons for that. Then what happens is you identify and define the independent and dependent variables. So for example, in a geometry application, you might have a circle drawn there, and you might define the independent variable as the radius and the dependent variable as the area. Of course, the area depends on the radius, and data capture can be used to analyze and, of course, verify the relationship between those two variables. Then what happens is those two variables, as you change them, you can output them into a list variable each, which goes into the lists and spreadsheet application. And this is where the data capture comes in. So in the list and spreadsheet application, you'll create two lists. And then what happens is you collect the data by modifying the independent variable, which of course will change the dependent variable and put that into the list and spreadsheet. Then what happens is you can create a scatter plot of those two list variables, and you can see the relationship between every radius coordinate, for example, compared to the corresponding area coordinate. And then what's even better is you can then analyze that result using the analytic solution. So, for example, us as teachers and students, we all know that the area of a circle is related to its radius via a equals pi r squared. So what you can do is you can superimpose the analytic solution, which is pi r squared, over the data capture the data captured points, and then of course verify that the answer is correct. So as you can see in this diagram over here, this is relating to the previous data capture, the previous animation that I showed you before. And I've got the blue dots, which is the data capture output, and the brown graph that's drawn there is the analytic solution. So of course you can see a match there, which is of course very good. So today what my plan is to show you how you can use data capture in simple situations such as verifying perimeter area volume formulas. And then something which is really, really nice, especially when you're teaching sine, cos, and tan graphs in year 11 or year 12, is to show how the graphs of sine, cos, and tan get generated. And then I'm going to introduce to you how you can use data capture to show how the derivative of a function is made or how it's derived. And then we're going to get ahead into more heavy optimization where you start looking at larger functions, etc. And then finally, I'm going to finish off with the area under a curve being represented by the integral. So let's get right into it. So what I'd like to start off with is to show you how you can verify that the area of a circle is pi r squared. So what I've done is I'm going to do everything on the computer software. To be honest, trying to do this on the handheld will be a bit tedious and a bit clunky. So if you are trying to do this, it might be best to do it on the computer software. So what I'm going to do is I'm going to start off with going to the geometry application, and it creates a blank screen over here where we can start drawing shapes. And I'm going to start by going to menu, then shapes, and then circle. I'm just going to draw a basic circle as follows. Then what I'd like to do is to represent the radius. The way I'm going to do that is via a line segment. So to get a line segment, I'm going to go to menu, points and lines, and then segment. So this line segment will connect, of course, the center of the circle to any point on the radius, any point on the circumference, sorry, and that forms our radius. So I'm going to get out of that mode, and as you can see, I can grab any part of the circle, make it large, make it small, and the radius, of course, expands and contracts as appropriate. So what I'm going to start off with is I'm going to, first of all, measure the radius. So I'm simply going to right-click this line segment, go to measurement, and length. So there you go. Right now, the measurement of that is 5.84 centimeters. So the calculator automatically creates a scale up here at 1 centimeter for that particular length over there. So it's, of course, use that scale in measuring the 5.84. What I'd like to do now as well is determine the area. So I'm going to right-click the circle, go to measurement, and then go to area. So as you can see, it's given an area of 107. So of course, there's some decimals hiding behind those numbers over there. But for our purposes, it should be fine. This is just a display. When you store these variables in the calculator's memory, it will store as many decimal places as it can handle. So what I'm going to do now is to define this 5.84 as the radius and the 107 as the area. So the way I'm going to do that is right-click the 5.84, like so, and go to the store. And now what the calculator does is it asks us what do we want to store the radius as. So I'm just going to call it RC. So RC for radius coordinate, because I'd like to eventually plot this as radius versus area. So now you can see it's saved it as radius, and I'm going to right-click the 107, store that, and put AC as area coordinate. So what you can see now is as I expand and contract the circle, these variables will start changing. Now the thing is, I haven't done any data capture yet. So currently, all the CAS is doing is it's tracking, it's changing the radius and the area one at a time, but it's not actually keeping track of those changes. It's every time I change it, the new value replaces the old one. So what data capture does is it avoids that problem, and every time either of these two variables changes, it will create a new entry for that certain variable. So the way we're going to do that is to create a new list and spreadsheet page. So Control-I to create new list and spreadsheet, go to number 4. And what I'm going to do is I'm going to go to column A and give that a name. This is the list variable name that I mentioned previously in my slides. So I'd like to track the radius value. So I'm going to call that rval. Just one bit of advice over here. Do not call this this variable over here. Do not try and call it the same as before, such as rc, because then you don't want to change your radius coordinate on the graphs application and don't want to mix it up with this one. So that's why I typically use C on the graphs or geometry page, and I put val on in the list and spreadsheet. So rval over here, and on the other one, I'm just going to put a val. So what this will do is in this column A, it will the TI-Nspire will track all the different radii that I will go over in 1.1, and in B, it will track all the areas. So this is where the data capture now gets used. So I'm going to go to the formula cell, the equals cell here in column A, press menu, data, and then data capture. So now it's going to ask for automatic or manual. For our purposes, it's always best to go with automatic, because that automatic will trigger a new data capture entry every time the radius or the area changes. So I'm going to press enter on that. And now the CAS asks, what variable do you want to track? Of course, I want to track the radius. And if you remember, the radius value on the circle was given by RC. So I'm going to find that, press enter, and there you go. So right now, the 6.3786, so on, that is the current radius value on the graph screen. If I now go to column B, I'm going to repeat the same procedure. Menu, data, data capture, automatic. However, this time I want to capture the area value. Hit enter, and there we go. So what this is saying is that currently our radius is at 6.37, etc., and the corresponding area via a measurement is 127.82, etc. So now what you'll see happen is when I go back to 1.1 and I increase and then decrease the size, aka the radius of the circle, and I go back to 1.2, suddenly I've now got all these new values that have been captured by each change that I've made on this circle. So that is the data capture at play right there. However, I'd probably advise against doing that too quickly, like as I've done over here, because what you really want to do is actually visualize the change in area as the radius changes. So if you find that you've done a data capture sort of prematurely, what you could do is head back to the formula line as follows: right-click and simply clear the data. So as I'm doing right now. So what I've got is I've cleared all the data, and currently the only data available to the Nspire is the 7.23 and the 164. The reason I'm doing that is because I want to actually plot the area versus the radius. So the way I'm going to do that is go Control-I and then add graphs to it. So what we're going to do is we're going to graph a scatter plot of the area versus the radius. So currently we're in function entry mode. We want to change that to scatter plot. So I'm going to do that by menu, graph entry, and scatter plot. So now it asks for a list of X values and a list of Y values. Of course, our X values for us today are going to be the radius values, and the Y values are going to be the area values. So just a quick recap, I keep pressing the var button over here because this gives us a list of all the appropriate variables that we have defined in the memory of the calculator. And now hit enter, and you don't really see anything because currently I've got a radius of 7.23 and an area of 164. So just to maybe make this a bit more useful, what I might do is change that -10 to 0, change that also to 0. I'll maybe make the maximum x value, that's already 10, that's fine. And for y value, I'll make that, let's say, about 350. So what you can see at the moment is I've got this 7.7 and so on radius, and that coordinate is sitting right there because there's only one value. So what I'm going to do is, before we get any further, I'm actually going to merge page 1.1 and 1.22 together. I want to show how the data capture dynamically updates everything. So the way I'm going to do that is I'm going to press Control up, and now it shows a summary of all the pages that I've got open. What I'm going to do is I'm going to right-click the first one and group it. So what it's done now is it's gone and it's grouped both the geometry application, as you can see here, with the graphs application there. So here is where the data capture really shines. I'm going to grab the circle and start making it smaller. And what you can see on the right-hand side is that the plots or the points that the data capture has captured are literally capturing all the values of the radius and the area as I change them. So I'm going to take it all the way down to as small as possible, which is down to 0. And I'll grab it and make it as big as possible. Maybe up to 10 might be good. Let's see if I can get it there. There you go. Managed to get it just past 10. And then if you can see any little gaps such as this or this on your graph, you could of course just grab it and slowly try and fill in those gaps. But there you go. This is the data captured data of the area of the circle as the radius changes. Of course, you can do nice things like changing y to things like a to capture the area, and the x at the bottom over there, I can change that x into radius and that sort of thing. I think where the power of doing something like this comes in is verifying this with the analytical solution. So with we know that the analytical solution is pi r squared. So what we could do is maybe change the graph entry back to pi x squared, back to function mode, and then I can just type in pi times x squared. So what I'm asking the CAS to do is to plot y versus pi x squared and see if the captured data agrees with that analytical answer. And I hit enter, and you can't really see anything going on there because it's the same color. So what I might do is change that to red, maybe. So change that color to red, and there you go. You can see that the analytical graph over there, which is pi times x squared, literally agrees with and superimposes onto the data capture that we did before. So this is a really good idea to show students such as in year 9 or maybe even year 10, just to show why the formulas are the way they are, and the fact that you've got a practical demonstration of, I won't say the proof of it, but really a demonstration of the validity of the formula as it is. So that's how you can use that for something like a circle. Now what I'd like to do is I'll quickly go over how you can do it with trigonometry, because I feel that this is something that a lot of people would find a lot of value with, which is taking a unit circle and then showcasing how the trig graphs come out of that. So what I've done over here is I've gone to a brand new document over here. As you notice, I've got document 3 at the bottom here. And what I want to do is I wanted to basically create a brand new one that has no variables linked up with the previous one. So I'm going to create this new one over here, and I'll go to graphs, the graphs page. And what I'll do is simply create a unit circle. So to create a unit circle, I'm going to go to menu and then to graph entry. I'll go to relation over there and simply type in the equation of the unit circle, which is x squared, let me get that right, plus y squared, and make that equal to 1. So there you go. There's our unit circle. Just to make things look a bit better, I'll just increase the axes over here. maybe change that scale to 1, change that to 1 as well. So now it looks a bit cleaner, so it's ready to go. So of course, when you're talking about trigonometric graphs, the multiple variables that you've got, or at least the main independent variable, is the angle made between the x-axis and your line. So what I'm going to start off with is, first of all, create a line segment, as I did before. So menu, geometry, points and lines, segment, and go from the origin over to any point on the unit circle. Let's say maybe that one. So now what I'd like to do is to create the angle over here as the independent variable. The best way to do that would be to go via menu, then geometry, and then measurement, and let's do directed angle. So directed angle is nice because it forces the direction to be anti-clockwise, as I'm showing right now. So I'm going to go from the right endpoint of the unit circle over to the origin, and then over to the angle line right there. So what I've now got is I've got the angle. As you can see, it gets tracked along this way, and it keeps going, and then it wraps back around. So we're pretty much only going to track from angle 0 all the way to angle 2 pi. So the thing is, we actually need the coordinates of that point over there in order to be able to track the values of sine and cos. So the way to do that, if you have a point and you don't have the coordinates, the best way to do it is simply to hover over the point, right-click it, go to coordinates and equations. And what it does is it's now given you the coordinate here. Of course, as I grab the point and move it, the value of the x and y coordinates will change, of course. So how are we going to data capture and track everything going on? I'm simply going to right-click the angle, because that's our main variable, store it as simply th for theta. Likewise, I'm going to go to the x value here, right-click that, store, and store it as x coordinate, xc. And right-click the y value, store that as yc for y coordinate. So now what's happening is as I drag the point around the unit circle, I've got the angle theta being connected to the x value of the coordinate and the y value of the coordinate as well. So what we could do now is create a list and spreadsheet, and maybe let's do one for theta versus the x value so we can look at cos. So Control I, list and spreadsheet, and up here I'm going to type in th val, so the value of theta, and over here I'm just going to put x val for tracking the x coordinate. So as did before, I'm going to go to the formula cell, go to menu, data capture automatic, go to my list of variables, and then go to not xc, sorry. I want to track my thetas. So var, and maybe let's go to th. So that's my theta values there. Hit enter on that one. Then go to the B columns formula cell. Then go to menu, data capture, automatic, and let's track the x coordinate, which is right there, and hit enter. So what I've got is an angle, a theta angle of approximately 1 radian, corresponding to an x coordinate on the unit circle of about 0.54 and so on. So what I'd like to do is to create a graph along with this that will track the values of cosine of theta, because the x value of the point is cosine. So what I might do is create a new graphs page directly after this one. So Control I and make a new graphs page. And before we do any data capture in here, it might be a good idea to actually set up the axes appropriately. So the way I'm going to do that is I'm going to go to -10, change that to 0, change the 10 to 2 pi, because we can only go from 0 to 2 pi. I change the scale over here to maybe pi over 2, just to showcase the important points. So with 0, pi and 2 pi, 3 pi and 2, etc. And on the y values, I might go up to maybe, let's say, 1.5. And below, let's go to -1.5. So now I've got my axes ready to go, really. Let's make that maybe 0.5. Yep, so I've got my axes ready to go. and actually make that 1. That's probably a bit better. Yeah, my axes are now ready to go, and let's put the scatter plot in. So menu, graph entry, scatter plot, and to collect all the x values, I'm going to go to variable, which is theta. Y, I'm going to make that x val, which is all the x values. Hit enter, and I've got a certain point over there. Of course, that point by itself doesn't really mean much, so let's maybe group these things together and see what's going to happen. Then go back to 1.1, control up, right-click, and group them together, and now I've got this happening. Okay, so of course the unit circle doesn't look too good because of the scale happening. So what we might do is maybe just change that to, let's say, something like 2.5 and make that at negative 2.5. That looks slightly better. I'll move the coordinate out of the way and the angle out of the way as well. So we've now got a clean circle ready to do this. So what's probably the best thing to do is take that point and maybe go to the to angle 0 like this. So I've got the point over there, and I've already got something over there. So when you're setting this up for a class, you might have the graph set up and you have some data sitting there already. It might be a good idea to go back to your spreadsheet and simply clear all the data that we created before. So now we've got a fresh start. I'll be able to grab that point over there and rotate it around the unit circle. So if I grab that and now start, let me just grab that point. There we go. That's a point on. And I slowly start increasing the angle. What you can see is as the angle theta increases, we get the cosine graph as tracked by the x value of the coordinate. There we go. And that there is one full cycle of the cosine graph. As you can see, that's a very visual and dynamic interactivity that pretty much showcases in real time how the cosine graph gets generated. The really good thing is you can actually change this to a sine graph quite easily. You can go back to the data capture here, and you can clear all the data as I'm showing here. Instead of xval, you can actually double-click that and change that to a yval to track the sine values. And we can repeat the data capture steps, menu 3, 2, and 1. But this time we want to capture the y values of the coordinates. I hit enter on that, and it'll ask, do you want to, it'll overwrite data. Of course we want to do that because we're looking at sine rather than cos. And yeah, what's happening there?
Sorry to interrupt there, Stephen. I'm thinking you need the YC there, the Y coordinate.
The Y coordinate?
Yeah.
On this one here?
Yep, you put in yval when you were doing the, when you in your equals, in your formula definition.
Yes, so sorry, yep. So I need to put YC over there.
Correct, yep. Got it.
There you go. Thank you very much. Got it.
All right.
Excellent. So now that we've got that, we can now repeat the same deal, and you can see what happens. So I can grab this, and it should. Oh, sorry, I need to change the scatter plot over here. There's a lot going on over there, as you can see. So maybe change the scatter plot this time. Scatter plot, and instead of theta value and x value, we're tracking theta value and y value. And there you go. I've already got some data there. But let's just take it further, and I slowly rotate around the unit circle, and there we go, is our value of sine of x. So that's just a really quick, I reckon pretty easy way of showcasing how a unit circle produces the values of sine and cosine. For tan, it's pretty similar as well, though you have to create a vertical line over here, then extend the line and measure the y coordinate, etc., etc. Okay, so that pretty much concludes the sort of basics introduction to what data capture is. Brian, do you have anything to add to what I've done so far?
I've just got a few questions that are coming in there, and it's pretty good. A comment I'd like to make first up is you said right at the start that you were separating the RC, or in this case the XC, YC, for coordinates on your geometry page, and then when you went to the lists and spreadsheet page to then use the term val. I thought that was a very clever sort of notation to show the two different ways, because it actually is in your formula definition on the lists and spreadsheet page where you say equals, and you're saying what that column of values will be equal to.
Correct.
In the capture. So so we see that example. R val is equaling the capture of the R coordinate.
Yep.
And the one, I dare say, would just be the increment as it does it.
I'm pretty sure the one is for automatic. So that one over there tells the CAS that it's the automatic data capture. That's right. Yep.
Great. Yep. Because that was the other thing that you selected there, whether it was auto or manual.
Correct. Yes.
I've had some comments coming in there saying, but whether you set this in exact values or in decimal. Now, I'm seeing decimal here.
Yeah.
Yet in the graphs page, when you're setting the axes for the graphs and so the labelling on the graphs rather, it was coming up in exact value. For example, on the trigonometric one, we had...
that's right. Yeah.
And so forth. Is there a consideration there that should be... anything there that should be especially considered in your view?
Well, I guess the only thing to really consider over here is that when you're doing things on the graphs or the geometry application, most things are done in decimal form. So everything in exact form would be done on the calculator page. So things like this one over here, and grabbing that point and moving it around as follows. It pretty much tracks it in decimal like that. Now, in terms of the exact values that you see on the graphs page over here, really where that comes from is the fact that my calculator is in exact mode. So when I go to document settings like this, I've kept my calculation mode in exact. And fortunately, when it comes to something like graph axes, the calculator is pretty good at keeping things as best as it can in exact form. Any complicated surds or complicated fractions and that sort of thing, it'll tend to fall back to decimals. But in terms of these sort of things, it does a pretty good job if you set it up correctly, as you can see over here.
Okay, yep. And of course, the other way to do that is just put the settings rather than exact. You could put them in auto, which would,
that's right, exactly.
Show out, yep. So we saw the settings there. Auto can be a handy way of seeing that it comes the way we want to see them. Yeah, look, people are keen here. I'm getting lots of questions. Why did you choose? And I can see the graph page there. You've chosen to use a graphs page rather than data and statistics. I think I know the answer, but I'll let you. Perhaps I should put it to you as it has been asked.
Yeah. Why did I use a graphs page? Well, I think the primary reason I use the graphs page is because I can take the scatter plot that I've got, the data captured points there, and superimpose a function directly onto it quite easily. So the graphs page, of course, its natural concept to deal with is, of course, just putting a graph like this. And the way I'm going to do it, I can, of course, just type in sine of x as follows, and you can see that the graph of sine of x goes directly above it. Again, it's become blue. So I can change that to maybe red. Now, as far as I'm aware, I believe that the data and what is it? Sorry, the data and statistics page. Yeah, whoa. I'm fairly sure that you're able to get a graph on there as well. Though I'll be completely honest, my experience with this particular application isn't up to scratch. So yeah. So that's probably all I can add to that. Sorry about that. But
no, I reckon that's absolutely spot on. And where I know I have mostly been using data and stats, but you have actually directed me across to using graphs page more for this. I agree with you. It's a cleaner and an easier way to do it, but both page types can do it.
That's right, exactly.
it's looking good. I better let you get back to it. But before I do, I just ask one more, or refer one more question that people have been asking. In the software that you're using right click. How can that be done on the handheld if students are using the handheld?
Yes, okay, very good point. So to get right click done on the handheld, the button combination is Control and Menu. So
terrific.
If you press Control and Menu, and I think the easy way to look at it is there's that little blue icon above the menu button. So pressing Control and that will give you the right click. So I'm pretty sure that's probably the best way. The only way I believe that you can right click on the handheld. So that's good. Great question there, Brian.
Terrific. Oh, look, it wasn't from me. We've got a very enthusiastic group of participants online tonight. So that's
excellent.
That's great. Yeah. Just while Stephen's sort of setting up the next part of the activity, could I just mention that with the software, what I've found, and I know I see this with my own students, they're so eager to look at the new calculator when they buy it, they overlook the fact that they've actually paid for two calculators in one. Mm-hmm. They've had the handheld, what we refer to as the handheld unit, but also in that same packaging is a registration code for the software. And I think they're absolutely missing half of the product if they just throw that packaging away and don't install and register the software, because I find that each of them has their advantages. The handheld, sometimes it's great to be just driving things with your thumbs in a very small and portable device. But for more complex calculations, it's certainly easier to use the software environment.
The software, correct? Yes.
What's happening here, Stephen?
Yeah. Okay. So I think we're ready to go for a second round of some data capture, right? Yeah.
I reckon this is looking like it's going to be a favourite application of mine. I can love it.
That's right. Okay, so getting back to our data capture and calculus. So as you've seen, the previous couple of things that I've shown you, they haven't really been calculus related specifically. They've just been more of the intro to and general data capture concepts. So I'd like to switch over now onto calculus, the focus of tonight's webinar, and show you how data capture can be used to really demonstrate concepts in calculus. So the first thing is something called we all our favorite first principles concept. Us as teachers love it. Not sure about the students, but I know for me for sure. I certainly have a soft spot for first principles, especially given the dynamic interactivity that the Nspire gives us. So what I've got here is I've got a basic f of x equals x squared, just a simple parabola over here. And I've got this point over here, this black point that I've chosen, and I can move the point along the parabola any way I want. Just to keep things simple, I've forced it to be on 1. And as you can see, the green line over there is the tangent to the graph at a certainly chosen x point, and it's tracking the gradient over here. What I've also done is created a new point up here, and it creates a secant, or chord rather, between this black point here and that brown point there. I can, of course, start moving the point along the curve, and this pretty much showcases the first principles formula, which is to get the chord's red gradient to become the tangent's green gradient, you'd want to reduce your h value down to 0. So whilst this is not specifically a data capture concept, of course we can make a data capture by tracking the value of this red gradient versus the value of h. I think it's more it has more value to just show something this to the class and take draw those 2 points together. I just recently started calculus with one of my classes at school, and I think that the students really loved seeing seeing this over here, because in the textbooks and on the board, we can't really show concepts like this. The fact that it's so dynamic and interactive makes it an absolute winner in terms of just getting that concept fully understood. So that's one which is first principles, which will be included in your in the pack of resources that will be emailed out to you shortly. Brian will talk about that at the end of the webinar. What I want to talk about in terms of data capture is here's one that I've recently set up, which is, again, I've got the parabola here, but this time I'm going to be tracking the gradient of the tangent to the parabola at a given x value. So as you can see, I've linked an x value here with the gradient of the tangent. So if I grab this point right now and start moving along the graph, what you can see is on the right-hand side, I've got a scatter plot that, of course, is data capturing every x value and combining it or linking it up with the respective gradient value. Of course, I can take it all the way down to the bottom and then take it to negative x values, and there we go. So what we've done is we've done a data capture of the x value versus the gradient. And again, you can do a really nice thing. We've got a scatter plot here, and of course, later on when you show or derive the fact that the derivative of x squared is 2x, you can come back to this, this application, go to menu, graph entry, put a function there, and put 2x, which is the answer that you've derived analytically. Hit enter, and what do you know? You've got the function fx equals 2x being graphed over there. And of course, it superimposes onto the data captured points. And again, it proves it shows that the gradient or the derivative of x squared is certainly 2x, as shown by this data capture happening over here. The really good news is that you can go back here and delete or clear the data as I've shown previously. I'll probably maybe remove that f2x over there, and you can do something really nice. You can actually change this to, let's say, for example, a cubic. So I can change that x squared to x to the 3, for example. And what I could do, maybe just change this to a positive to make it a bit easier. Let's clear all the data there. Yep, back here. So I can change that f1x to something like a cubic, for example. And now I've got a cubic over there. Can maybe move the graph screen like this. Grab that red dot and then move it to start tracking the gradient. And as you can see, the way the data capture has been set up, it's simply tracking the gradient as I move along. And what you can see is as I move along, I end up with the parabolic shape here. And the beauty of this is that, again, I can go to my functions over there and simply type in 3x squared, which is the analytic solution of the derivative. Hit enter, and there you go. The analytic solution, of course, matches up with the scatter plotted data over there. So that's one possibility of using data capture. It's simply creating a tangent and tracking the gradient of the tangent along with the actual x value of your function. Just to quickly show you how that would be created, I'll just spend about a minute doing this. Maybe if I choose something like, let's just say x squared to start off nice and easily, what I'd like to do is create a point on there. So menu, geometry, points and lines, point on, and just choose a random point on the parabola as follows. Then what I'd like to do is create a tangent on that point by going menu, geometry, points and lines, and then tangent. And I simply take my my cursor over to the point that I previously put there and press enter on that. Now just escape everything, get rid of everything that's sort of in the way. And what I'd like to do is track the actual gradient of this tangent. Now, unfortunately, when I drew the tangent, the CAS gave us the equation of the tangent as opposed to the gradient. So to get the gradient, it's quite simple. We're going to go back to geometry, menu, geometry, measurement, and this time we're going to go slope. I'm going to hover over the line, and there we go. I'm going to place the slope right next to the line as shown. There we go. And what I've now got is, as I move the line, I've got the gradient of the line being tracked as well. So now when you're thinking of what to data capture, you can right-click or control menu, the X value, right-click store XC for X coordinate, and then this one, I can right-click store that as MC or MC for the gradient coordinate quote. So I've got that, and I can drag that along. And of course, I can go to a new list and spreadsheet and then start tracking the X value and then the M value as follows. Go to menu, data, data capture, automatic, variables, XC, enter, then go to the same box there, menu, data, data capture, automatic, and let's track the gradients, and there we go. So as I move this, I can of course get the gradient. So quickly showing you where that comes out of. You got menu, graph entry, scatter plot, and now let's plot the X values versus the gradient values. Hit enter, and I'll create a few more data points as follows, like this. Just generate a nice set of data. Go back to 1.3, and there we go. We've got 2x over there. So that's pretty much how I created this particular file over here. Of course, I started changing colors, etc. But that gives you a fair, easy idea of how that works out.
Great. I love it. Great visual. Yeah, just a quick one there, Stephen. Someone just pointed out that you could actually put those two graphs on the same page.
Correct. That's right. So I can change 1.3. Maybe I could move that left. Move that left as follows. Then go here and group them together. There we go.
Yep. Yeah, that's how you had in your first example. But they could in fact be both in the same application.
Same application? Yes, that's right.
Yeah. Split screen, yeah, that's what our viewer suggested. I'm not asking you to do it. I'm just saying that that can be done as well.
Oh, sure, can be done. Correct. Yeah, I can put this directly on the same graph over there.
It may make things look a little bit too busy.
Yeah, a little bit cluttered, yeah, but it's certainly possible. There we go. Yeah, and you can actually get the graphs as. That looks pretty cool, doesn't it?
I reckon it's very cool.
That's like very cool, yeah. Yeah, that's exactly right. So you can certainly do that. I think that's a really good idea. Thank you, whoever recommended that. I think that's a pretty powerful visual for students as well. So yeah, this is exactly what's going on. We've got the gradient, we've got the X value being tracked, etc., etc. Maybe I can remove that and so on. So yeah, so hopefully when everyone's trying out making one of these themselves, they're able to do it without any errors being popped up or anything like that. I think it's a pretty straightforward thing to do. You just have to get the knack of it. It can be a steep learning curve, but once you've conquered that, then anything is possible, as they say. So I'd just like to quickly finish off with a couple of things. We have these optimization questions, such as this, where you take things like parabolas and you place shapes such as rectangles inside them. And it's a typical sort of exam-style question where the students are asked to maximize the area of the shape that's placed inside the parabola. And data capture is really good for demonstrating questions like this. So I've actually got a parabola here. I've got the rectangle drawn inside there, and I've got my data capture ready to go. So I'm capturing my X coordinates versus my areas. I've got it linked to a certain value at the moment, and I've got an empty graph here ready to collect and show all the data. So if I go back over here and grab that gray point, and let's start changing this. So I'm going to take that all the way to the top and then bring it all the way to the bottom. As you can see, the X value and the area is of course changing. You can bring it all the way down to the bottom. And what you can see is that I've got all this data being collected from the previous screen. And when I go here, there, I've got all the X values being plotted against all the measured area values. What I've also set up here is a little slider that will superimpose the analytical solution as shown. So if I just quickly hover over, if I can get my, there we go. That orange graph over there is the analytical solution to the area of the rectangle as it varies around the parabola. And of course, this analytical solution can be used to figure out the maximum value and the X value at which it occurs, etc. But it can be applied not only to rectangles, you can do things like triangles as follows. I'll quickly get through this one. There you go, you change the triangles. And again, the data capture has gone and captured all the relevant coordinates and values, and it's plotted the actual points themselves. Again, you can verify that with the analytical solution. Just in case you wanted to see, the analytical solution looks like this. So I've got my my parabolic function over there, which is a parabola, and I've just multiplied that by x, which is what you'd get if you work it out with pen and paper. So f2 of x is the analytical function tracking the area. It's not just restricted to parabolas or graphs like that. You can even do things like circles or ellipses or bell curves or what have you. So the world is literally your oyster when you've got data capture at your fingertips, as you can see over here. I created these files a while ago, and I pretty much used data capture to showcase all these different ideas. I think it's a really good idea to use data capture as much as possible in your teaching arsenal. It just makes concepts so much more visual and so much more easier to understand. It's of course not all about just maximizing. You can also minimize as well. So here is a straight line on the Cartesian axis, and I want to minimize the distance on the line from the origin. So we want to find, for example, what's the minimum distance between the line and the origin. Again, I'm tracking the length of this particular line over here, which is there, with the X value of the point on the line. And I go over here, and there we go. It's gone and tracked all the different lengths versus all the different X's. And again, as you can see, there's a minimum over here, which of course can be discussed in class, how to get that analytically, etc. And finally, just to quickly finish off in the interests of time, integrals. Integrals don't really get too much of a mention with these because they're a bit harder to set up compared to derivatives, but they're still very useful. So what I've got here is I've got a cubic graph, and I'm trying to see the relationship between the cumulative area versus the X value of this point over here. So again, I've got my X values being tracked with the area values, and I've got a screen here ready to plot the scatter plot. I can drag this point here. I can drag it to the left of that certain x-intercept, which was -2. I can drag it to the right as follows, and I'll stop it at 1 just to be a bit careful. And what you'll see is that the area has sort of gone upwards like this. And then when I grab that point again and I move it to the right, what's happening is we're effectively collecting negative area. So what that means is that the cumulative area will now start decreasing, as you can see as follows. And then you can take it further to the right, and it will now start increasing again. So this showcases that the area that's being collected via an integral is simply a cumulative area as you move from left to right. Of course, I fixed that x-intercept over there as a reference, but as I move the right x value as shown, you can see that the value of that integral is changing according to the cumulative area collected as I've moved left and right. Okay, so that pretty much concludes the data capture webinar right there. Thank you for tuning in. I hope you've learned quite a bit of material that you can use with your classes. Thanks, Brian.
That was absolutely terrific. Thank you very much. Thank you indeed. I just think it was terrific that you started off with something that was fairly simple to start with, the radius and area of a circle, and then into the from circle straight across to trigonometry in the unit circle, differentiation by first principles, and then of course showing the derivative graph, which I really like, and I know I'm going to use, as well as the optimisation tricks, and then ultimately integration. You've taken us on a terrific journey there. Thank you very much, Stephen.
Hey, you're welcome, Brian.
Just on optimisation, it made me think of the Canberra. I don't know if we've got any listeners tonight from the ACT, but the Canberra Mathematics Association, their annual conference this year, which is in August, 17th of August. Their theme is optimisation. Optimisation, making the most of maths. So
awesome.
If you're not doing anything then, Stephen, and yes, as I said, the LECs, if you enjoyed this presentation, I really would encourage you to get along to one of the Learn, Energise, Connect events, either in Preston at the end of the year in December in Victoria, or I know we have such similar events happening in Brisbane and some in South Australia as well. I'm not sure about possibly also Western Australia and Tasmania. So keep an eye on those. Just closing us out now. If you do have any last-minute questions to type in, I'm sharing my screen now, so I won't be able to see them. But Stephen can. If not a question, you might just want to type in your words of thanks. You will, when I close the event, be taken to a page where we invite your feedback. Thank you very much in anticipation of that. And within a couple of days, you will receive an email with all those clever files that Stephen has made. But of course, you know how to make them yourself now, as well as your attendance certificate. And best of all, if you'd like to see it all again, you can either look for this event on TI Australia's YouTube channel or access it through our own webinar section of our own TI Australia website. Now, you may have initially signed up because you received the e-newsletter from Texas Instruments Australia, but of course the other way to do it is to go directly to the website. I'm just going to show you how to do that, because on the website, there's our front page here, and you see here free webinars, register now. So if you click upon that, you have the two options to either watch upcoming webinars or click on past webinars, which you can watch on demand. So that will just go straight to your desktop. While we're here, I'll just give a plug for the two upcoming ones, Transformations, 1 week from today. And also, on the same date, you see here Curriculum Inspiration, Exponential Learning, and that's going to be exponential learning. That will be on the CAS platform. Curriculum Inspirations, that's a new series that we're running this year. They start at 4 p.m. Australian Eastern Standard Time rather than our usual 7 p.m. But they only go for 15 minutes. It's a quick take a look. These are the tricks. This is a quick activity, and if you hit the details here, you see our presenter will be Chris Orison. You get an overview of the session. We would ask that if you register for these Curriculum Inspiration webinars, that you would download the activity in advance. I'm just doing so now. And what this does, it takes you to a page. Chris wrote this activity especially for the webinar event, and you can download all the files by following the link here. So as I said, if you follow through, and that's for Maths Methods, if you follow through to register, then you will see that happens at 4 o'clock rather than the later time of 7 o'clock. Here we are here, 4 p.m. Australian Eastern Standard Time, and it just goes for 15 minutes. So just giving that one a plug as well. So So if you do have other further questions, phone numbers on your screens now for Australia and New Zealand. That's the Texas Instruments Australia offices. And once again, I would really like to thank Stephen for his presentation this evening on using data capture to help teach calculus. Thank you all very much for attending, and good night to all.
Okay, thank you. Good night.